Hello. So this is our last week for this course, and you made it. We're at the very end. The lectures for this week are basically just selected topics that you will not be uh, assessed on, no assignments and stuff. And so these are basically for just enriching your knowledge of our data structures, and we're going to introduce a couple more things this week. And just so that you're aware of some of the things that are, very much useful in reality, and we don't necessarily have the time to dive very deep into it. And so today, the topic is hashing. Now, if you have studied the, programming languages or beyond C++, you certainly have heard about hash table and that concept, what this is for. And so let's actually get right into this. And again, I'm using the excellent slides from the Introduction to Algorithms book. This is a very classical book and has a lot of great content in it. So let us start with a problem. So I know perhaps you have not taken class on compiler design. When you get to it, or like when you actually compile a C++ program, and one of the core data structures that a compiler maintains is called a simple table. And the simple could be your identifiers, your variables, functions, objects, classes, right, or namespaces. Those identifiers that you define in your source code, compiler has to maintain records of them for various different purposes. So the simple table, basically maintains a table of records. And here's an example of a record. Well, the record has a key, and it may have probably has other kind of satellite data. For example, the symbol type, is it a variable? Is it a function? It may maintain, attributes. For example, it's a private variable of a class, or is a public variable, things like that. Now, so how do we implement a simple table? Now, the operations we have to do on the simple table could be common things we want to do to add a symbol to it, right? Insert, or maybe once we're getting out of a scope for a particular symbol, we need to remove it. So that's a delete. And of course, we need to search it. When the compiler encounters a symbol, it needs to see, well, does it exist, right? Is this an old defined symbol or is it a new one? So question would be, how do we, organize such data structure? And one idea, pretty basic, would be maintain a direct access table. Now, a direct access table that basically is analogous to an array that you are familiar with. So here's an idea, right? Suppose the keys are from this set of sort of natural numbers between 0 and m-1, and just so that we'll have a m number of keys, okay? And then the keys are distinct. We're starting off with a simple problem, right? And then we're gonna set up an array, t subscript k equal to, if it's x, if x is within the set of a key k, and the key of x is k. So essentially just using the key of the records as the index in the array, basically. Now, if the key doesn't exist, then we'll simply say, well, it's nil or null in that cell. So essentially it's just like using an array structure to store the records. And the array indexes are the keys of the records. And so we're assuming the keys are actually drawn from a, several natural numbers, right? Just, simplify the simplest problem first. Of course, the lookup, the operations that we previously talked about, insert, delete, and search, that will be basically constant time. And there's only one problem, right? The range of keys can be very large. Even let's talk, say we, talking about integers, and then on a 64-bit system, we have a huge number of different keys. If you just matching the key with array index, how big that array is going to be? So it may not be practical, right? What if we are trying to, in the original problem, a simple table, the key of those records, obvious choice would be the symbol name, or some format of it, right? The symbol name, if we use the symbol name, is actually character strings, then the range of keys is even larger. Suppose we devise a method to translate that into a number, okay? So that is a problem. Using a direct access table, it doesn't seem to work very well. So here's another method to do it. We use hash functions. Now the name hash function, hashing seems, the idea of a hashing is this, right? So hash function H to map all the keys into a small set of numbers or slots in the table. So we have table T, and then we're going to have M slots of the table. And then we have many keys. So there's a universe of keys, which can be quite large. And then you have an actual set of keys that you are using. And those keys, let's say we have 5 of those, and we're going to hash, basically map them to the indexes in the table T by applying a function. And so, for example, for key one, K1, that key, we apply this H function, and then we get a number that points to this particular slot. This essentially 0, 1, is the second, well, the slot number 2, okay? And of course, here's the thing. We have M slots. Since we have M slots, but we have actually more keys than the slots, not just 5. Typically, we should have more. And then, we have to basically have the possibility that multiple keys will be mapped to the same slot. So here's a situation where K2 and K5, their hash value are the same. So H of K2 equal to H of K5. And so they are put into the same slot. So when a record to be inserted, into the maps to an already occupied slot in the table T, a collision occurs. So this is called a collision. And what are we going to do about it, right? We'll have to handle that. So one way to handle collisions is by chaining. Now, chaining is simply using a linked list to hold on to the records where the hash values are the same. And, for example, here, the H of 49, H of 86, H of 52, they're all the same, equal to this slot I, okay? And then we just put them into this linked list. And this is the one way of doing it. So there is a problem with this, okay? In the worst case, every key hashes onto the same slot. And that would be obviously the worst case, because then effectively your hash table is a linked list. So this is basically the worst case. Now, of course, we don't want to get to the worst case. Now, let's actually do an analysis of the average case. The average case of chaining. Now, we make an assumption. Let's first start with an assumption of a simple uniform hashing. So each key, K, within the set of S, which is the set of keys that we need to put into the table. So each key is equally likely to be hashed to any slot of table T, independent of where other keys are hashed. And so this is a nice property we want to have. So when we do some theoretical analysis of the performance or distribution of the keys, when we talk about chaining as a way to resolve collision, and so this is one property we want to use this as a foundation to do analysis. So it's called a simple uniform hashing. This is the property. It's desirable. So now let's define a couple more parameters. Let n be the number of keys in the table. So meaning we have, that's the size of S, right? So that's the number of keys we're dealing with. And then let m be the number of slots, okay? Remember that table, we have that many slots. So we introduce a new parameter. It's called, the load factor. So the load factor of T would be, we use alpha. So alpha equal to n over m, okay? So n over m is basically the average number of keys per slot, right? So what is the cost of searching in this table? So the expected time for a unsuccessful search for a record with a given key is basically theta of 1 plus alpha. Now, in the book, there's more details about this, but intuitively, here's what we can think about. It takes constant time to apply the hash function to access the slot. And then to search the list, right? So essentially, let's say if there's an unsuccessful search, and we know the average length of the list is alpha. So it could take that much time to actually search the list, right? So that's basically 1 plus alpha. Now remember, this notation really just means that if alpha end up being a function that's more than the constant time, and then we will basically say that's basically the, here's an example, right? So we actually say expected search time is theta of 1, constant time. This is a special case. And in fact, this is probably a desirable case in reality. If alpha is big O of 1, and we are upper bound of 1, and it's a constant time, if basically we're saying if the size of the table grows proportional to the size, the number of keys, which is probably what we want. So if that is the case, which is most likely the case in reality, then the expected search time is theta over 1, is constant time. So that's nice, right? That's kind of what we expect with hash tables. Now, a successful search, this is the other case. What if not one of the cases where you cannot find the key because it doesn't exist, and then when the key does exist, how much time does it take to search the key that exists? Well, it's a little more involved. The book has more details, but it turns out, it's has the same asymptotic bound, essentially the same thing as this for the unsuccessful case. Now, question comes, how do we choose a hash function? to actually maintain that, you remember we said we have a property we want to maintain is the simple uniform hashing. We use that as a basis when we get to talk about, in fact, these things are the way we can get to these numbers to analyze the complexity, time complexity, is based on that property. And so we want to say, we want to get the hash function that will give us that simple uniform hashing. So the reality is that assumption is kind of hard to guarantee, but there are some techniques that can be employed so that we get to that guarantee, well, get to that property pretty well. Okay, so here's what we want, right? Good hash function should distribute the keys uniformly into the slots of the table. So regularity in the key distribution should not affect this uniformity. Essentially, of course, we don't want the hash function, right, to have all the keys put into a small number of locations. Well, of course, we want to distribute them widely across the table. That would be a good situation. Uniformly into the slots of the table, so that the chains are shorter, right? And that means less search time. And the key distribution, even if the keys are distributed with some kind of regularity, some kind of pattern, that should not affect the uniformity. So the hash function needs to be so good that you want to maintain these things. And there's different ways, of course. So let's look at a couple of simple methods. One is called the division method. Now the division method, it's a simple heuristic-based method. So assuming all keys are integers, now if the keys are not integers, there's a way to turn them into integers, right? So assuming they're integers, then we define this hash function to be, key modulo m. Now remember, m is the size of the hash table, or the number of slots. Now we have to be careful how to pick m. How do you decide what m is, right? Say you have a million keys. How do you decide what m is? Well, we know a couple of things that are not good. First of all, don't pick an m and that has a small divisor d. Now, this just based on math, we can figure out there's certain things you don't want to. Then also you don't want a majority of the keys that are somewhat close to a modular d, some kind of divisor, and that also can affect the uniformity. In an extreme case, here's an extreme case. If m is actually a power of 2, right? If it's a power of 2, then the hash doesn't even depend on all the bits of the key. Now here's an example. So if you have, let's say in a binary form, this is the key, and m is a 2 to the power of 6. If you do that with a modulo operation, then the hash value would be simply just the last 6 digits, right? And that's actually not good, okay? So what do we do then? So what we know is it's a good idea to pick m to be a prime. And also make sure that prime is not too close to a power of 2 or 10. Or not otherwise used prominently in the computing environment. We essentially just want to make this hash function to be very much independent of whatever the keys you get. There are some issues here. So picking a table size, make that size a prime is actually inconvenient. But this can be done, and you can use it. They give you reasonable performance. Now, there is a better way though, and let's see. So in the second method is a multiplication method. Again, this is another heuristics-based method for designing hash functions. Now, again, assume all the keys are integers. And now we say m is actually a power of 2. And assume the computer has W-bit words. So if you're on a 64-bit computer, that would be 64-bit. That's the size of a word, a computer word. And now we can define a hash function like this. Looks a little involved, but this RSH is a right shift. And A times K modulo 2 to the power of W, all right shift, W minus R. And so where this, RSH is a bitwise right shift operator. Now A, we'll have to pick an A, and the A is an odd integer in the range of 2 to the power of W minus 1 and 2 to the power of W. And so that's how you want to pick a good A over here. Now, we don't want to pick A too close to the boundary of the range. And the multiplication modulo 2 to the power of W is fairly fast, right? Compared to the division method, because this is actually a very efficient operation. And the right shift operator is also pretty fast too. Well, depending on the chips, the instruction set, this could it be just one instruction or just a very few number of instructions to get it done. And let's take a look at an example. Suppose we have m equals to 8, which is 2 to the power of 3. So 3 is R, okay? No, 3 is W. So the R, let's see, W bit words, 2 to the R. Yeah, R, so excuse me, R is 3. So that small r is 3, and W is we have 7 bit words. So suppose we have 7 bit words, W is 7. Then we want to pick an A, and let's say suppose we pick an A that's basically within that range, okay? And that's a number that's within that range. And then given a key of this, we multiply them, and then modulo 2 to the power of W. What happens is essentially taking the R is 3. We're taking the 3 most significant digits of the second word of the result of that multiplication. And this modulo wheel here is essentially just a visualization of the modulo operation. And I'm going to skip that for now. And this doesn't really necessarily matter too much here, but you know what a modulo operation is. So that's basically the multiplication method, and there are actually many other methods. So we're going to just move on to a different method of handling collisions. Now, Peter said, well, you can handle collision with simply a linked list. Maybe not just a linked list. Sometimes you can use a treat as well. In fact, the real world application may end up, picking a hybrid strategy, like depending on the size of the table, and it may use different methods. And so that is the real world application. But now here we're just talking about the theory behind those things, and the reality can be a little more complicated. Now, there is another way to resolve collision. It's called open addressing. Now, what's open addressing? Open addressing means, well, I'm not going to use a linked list. All the elements, all the keys are going to be within the table itself. I'm not going to actually attach a list or attach some other data structure with it. Okay, so the insertion, here's how, what we do here instead is we probe the table, right? We systematically probe the table until an empty slot is found. So we have some kind of probe sequence, and you know, and check in the table until you find an empty slot. So that's the kind of the idea behind this. So the hash function now depends on both the key and the probe number. So we have a probe, you know, number, let's say 0, 1, all the way into m minus 1 because there's only m slots available in the table. So at a maximum, we probe m times. Well, obviously that would be a really bad situation. But anyways, that's what can happen. So we're gonna have a hash function that's gonna apply these two inputs and then produce the slot number. So the probe sequence, you know, we want the probe sequence to be a permutation of the, you know, numbers from 0 to m minus 1 because we want to make sure that basically every slot is a probe. Like they produce a distinct slot number to probe, right? You obviously don't want to keep probing the same slots, and because, you know, that's very inefficient. If that slot is occupied, you keep going back to the same thing, and that would be a waste of the computation. So you want that, you know, as a property of the probe sequence, you want to actually, you know, be able to probe different slots, right? So the table may fill up, and the thing about this open addressing strategy is that deletion can be a little difficult, although it can be done. But then when you actually, if you do need to delete the keys after they're inserted into the table, then you probably want to just go with the chaining method instead of the open addressing method. So here's a little illustration. Let's say I want to insert the key 496 into this hash table. So what we do is we start with the probe 0, and probe 0, let's say it gets into this slot number. So the hash function actually produces this slot number, okay? And well, it looks like this slot is occupied. So we'll move on. Now, then probe number 1, we encounter, let's say, this slot. Well, it's also occupied. And then probe number 2, oh, great, it was empty, right? It was empty. And now we can put this 496 right here. We found an empty slot, and this is where it goes, okay? So when we do the searching, so once that's done, now we're gonna search the key 496. Now we should use the same probe sequence, of course. So we apply the same hash function that produce the same probe sequence. So essentially, you know, the probe 0, we look at this, it's occupied. Probe 1 is over here, is, you know, it's something else. And then probe number 2, well, of course, this is how we inserted it previously, right? So at this step, now we have the same number of probes to find the key that was inserted before. So the search uses the same probe sequence. It terminated successfully if it finds the key. And if, you know, if it encounters an empty slot, let's say it just keeps probing and then you find an empty slot, that means it's unsuccessful, it can terminate. Why? Because if when you, if the key was, you know, basically if you were able to find an empty slot, that means the key essentially would have been inserted, right? So it's the same probe sequence, because now if you find an empty slot, right, when you try to insert, suppose we try to insert that key 496, and then somehow we leave, we'll find an empty slot, and then we need to actually put that key into that slot, right? It will not be empty. Now when we're searching for it, and we actually find an empty slot, that means, you know, that key was not inserted. So there are different probing strategies. How do you design your hash function to produce that sequence of probes for your insertion, for the search operations? Well, a naive method is called a linear probing. The linear probing uses this hash function. So this essentially, we're going to use another hash function, prime, h prime of k, as we discussed earlier, right? Use some function like that. And then plus I, which is the probe sequence number, right? And the modulo m. So this is simple. This will give you the property of producing a permutation of the slot numbers. Basically, you can hit all the slot numbers if you keep probing and until the end. So, however, it has a problem. The problem is called primary clustering. Essentially means that the occupied slots build up. So essentially, as you do probing, subsequently, you take a longer time to find empty slots. So that's the problem with the linear probing. And then another type of a probing strategy called double hashing, which is a very good probing strategy. So what we do is we use two ordinary hash functions, h1 of k and h2 of k. And then we combine them in this fashion, right? h1 of k plus I times h2 of k, all modulo m. And so this generally produces a very good result. And we have to be careful here. The h2 of k must be relative prime to m. And there obviously one way to make that happen is to use a power of 2 for m, and also make sure that h2 of k produce only odd numbers. Okay. So this is called double hashing. So let's do a little analysis of this open addressing strategy. How good is it, right? And now, as a theoretical analysis, we also first design a property that we want, and that property is called a uniform hashing. Uniform hashing says each key is equally likely to have any one of the permutations as is a probe sequence. Now, of course, there's m factorial permutations because this m is the size of the table. And we want to say each key is equally likely to have any one of the permutations. So you don't get into that clustering problem because like somehow, you produce the proper sequence, they're somehow all sharing the similar sequences, and that's going to be a problem. And then, you're trying to fill the keys into the same number of buckets, right? The slots. Excuse me. And now it can be proven. There's more details in the book if you're interested. And again, we'll look at two situations for search: unsuccessful search and a successful search. So suppose we have a open addressed hash table with a load factor alpha less than 1. Okay. Suppose we have a load factor that's less than 1. And well, we want this to be somewhat less than 1 because remember, all the elements, all the keys are put into the table. Obviously, your table has to be able to hold all the keys, right? You have n number of keys, so the table size has to be at least n, perhaps a little bit more. Okay. So with that load factor, the expected number of probes in an unsuccessful search is basically at most 1 over 1 minus alpha. Okay. Which is what does that mean? This is actually a pretty good number. And I'm going to skip the proof for now, and you can read more about it in the book, which describes in great details. So if alpha is constant, What that means is if alpha is constant, then accessing an open adjusted hash table takes constant time. Okay. So, remember, so basically the expected number of probes, if alpha is constant, of course, the search is also going to be constant, right? And so if the table, here's an example, right? If the table is half full, then the expected number of probes is 1 over 1 minus 0.5 and equal to 2. So on average, to find a key, find or insert a key, right? It takes about 2 probes, which is very good. Now, if the table is 90% full, then the expected number of probes is 1 over 1 minus 0.9, which is 10 probes. Well, not very good. So, I mean, in reality, what you might do is if the table gets to a certain level of fullness, I don't know, maybe 80%, 90%, perhaps, we essentially, basically make the table bigger, perhaps, right? You can grow it, and then you have to copy the elements over, and so that can be expensive operation. But it can be done perhaps efficiently. Just think about how vectors implemented. You keep adding elements until the array cannot hold it no more. It needs to reallocate a larger array, right? So, of course, so in real life, there's obviously a lot more to it to make a really efficient hash table. Now, this is basically in terms of introducing you to the concepts of hashing and just understanding. There's actually more to this, but hopefully this will get you some basic understanding what hash table is about. And let's take a look at the one in the C++ standard library. And we do have hash table implementation in the standard library. And so that would be the unordered map. Unordered map is a associative container. That's what it's called in STL, and or sometimes people call it the key value pairs, right? And so this, as a template parameter, it has to take a hash. Basically, take a hash object. It's a function object, and that hash will be used to produce the hash of the keys. And so, and then this or the map, and then you have used this. So we have, again, using this is a fairly straightforward, but behind the scene, it is a hash table. And now the exact implementation, it's very much implementation dependent. The standard really doesn't specify how you're supposed to implement. So the real implementation, it would be, a different compiler may have different implementation. And then they, but typically they should offer, very decent performance. And for some of those major compilers, you can basically, for your general purpose application, you should not have to worry too much about it. Now, this unordered map is going to use a hash function that's basically defined as a function object, standard hash. And this hash is, you can use this in your program, obviously, and this is defined as a template, okay, template type. And the basic types, they're already defined for you. And it also supports the string types, okay? Now, what you can also do, though, you can have your own hash function implemented for your specific types. So perhaps, actually, generally, that would be advisable if you have your own type, but let's say I have a structure that has 2 variables, first name, last name. You may want to define your own hash function, something, for example, like this. Okay, this is just an example. And so you just need to make sure you implement this, function operator, right? Function call operator. This is basically what makes this into, a function object for that satisfies the hash requirement. And what you do is simply combine, right, using the standard hash algorithm for each variable of your structure, and then you combine them somehow. And it's just one way to combine, very straightforward, but then it may not necessarily be the best. So typically, when it comes to combining hashes into a single hash, um, it's advisable to actually use the Boost library. And I did mention early this course that the Boost library is a very good library that extends beyond the standard library of C++. And in fact, many of the Boost libraries over time get standardized. And so there's even the C++ standard committee members on that Boost project. And so there's this Boost, hash portion of the Boost library has many of the utilities that you may consider using if you are dealing with, in your particular application, you need to deal with your hash situation. So if you want to put your own custom objects into the hash table, and then you might want to consider using the Boost library to combine hashes and have your own, good hashes. But you can have just a random, very, naive hash implementation. Problem is it's going to impact the performance of your hash table. As we noticed, if you don't design a hash function well, you could have the problem of the clustering or the really long linked lists, right? If the underlying hash table uses a linked list. So it's a good idea to use, something from, reputable libraries, unless this is your area of focus that your particular project wants to improve upon, then you may have your own specialized hash implementation. So that's all I have to say about hashing. And it certainly is not the end of this hashing topic, but hopefully I can get you to some basic level of understanding what is hashing is about. Now, just to give you an idea of the real world hashing algorithm, like the ones you see here, the standard hash function, that it's a generic hash function. And this hash function, as I said, is the implementation specific, and the standard doesn't specify exactly what kind of algorithm you need to use. So it turns out, as an example, like a GCC, the GCC is one of the major compilers of C++, and that uses a hash function just for those who are curious, and it's called a murmur hash. And this murmur hash is open source, and then you can find the source code of it. And there's actually a Wikipedia page here and describing what the idea of this. And as you'll see, the real world hash functions can be fairly complex. And so it's not very easy to design a really good hash function that's withstanding the test of time. But the ideas of what we said in the lecture still applies, and it gets you to understand what's desirable, what's not so desirable. But when it comes to engineering a really good hashing solution, and that's generic, that can apply to a variety of different kind of data types. And also there's things to consider about the collision-based attacks. There can be a sort of a denial of service attacks that you can read about if there's a vulnerability that, when it comes to designing a good hash function, there's a lot of things to consider in the real world, okay? So use standard library or a very reputable library like a Boost for your needs, unless, it's something that you are specifically looking into implementing a good hash implementation. Otherwise, use what's out there, okay? All right. I'll give you another lecture later on Wednesday about a different topic. We'll look at balanced trees. So this is for hashing today. Thank you.